grateful for this talk. I've been pretty excited about it, and many of you have probably heard me. You've probably already heard half the talk if you've been talking to me in breaks, so I apologize for that. Hopefully it lives up to the hype of being the last talk. So this is kind of what we're going to go through here. I've already talked about Sierra a little bit. We'll go into some more details. And then essentially I'm going to walk you through our grand experiment and the processes, kind of the challenges we've hit and the things that we've overcome and are trying to overcome next. Sierra has a historically very old build system, and we are trying to take it from one of the lagging or one of the older ones in the complex to maybe one of the more progressive ones. So we'll go through that. So Sierra, what is this thing? You can tell by the logo, it is very hard to just communicate what it is because it's an amalgamation of many different things. Essentially, in a nutshell, it is a multi-physics software suite that spans the continuum mechanics space. On top of that, we have meshing, optimization, coupled codes, V&V workflows, there's just a bunch of things globbed in here. We have over 70 active developers and over half a dozen teams and sometimes we even have to ask ourselves, well, who is currently living in Sierra and not, kind of a thing, because there's just so much activity around this. It also has multiple levels of access control within it. We have our own internal work, and then we have external collaborators. We have a very large customer base. It basically spans the entire US government, as well as people in industry and international partners. We are targeting the exascale machines, heterogeneous hardware. And Sierra has been around in kind of the same range as Chris was talking about. We're over 20 years of history and development here. In terms of the software architecture, this is and has been for a while, a monolithic Git repository, and before that, I think it was SVN, and before that, I don't want to think about it. That's not my purview. I'm looking forward. It has a monolithic build right now. So basically there is one build for all of this stuff that happens. And it is all very custom. So we have basically a forked version of BoostJam from a long time ago. And then that plus Make plus Ninja gives you the mega build of Sierra. And we are trying to move this into a CMake plus Spack ecosystem. So what does this look like today? So as I mentioned, it's one big build, and basically BJam does the configuration and kind of sketches out the dependencies. And then underneath that, we then assemble a bunch of make files so that way they can be targeted, or so that way they can be converted into target pools and rules that Ninja can digest. And then after that, we just turn it loose on the black box of Ninja. And out of that, we get this massive installation. And so this is also kind of exciting because this represents a nice opportunity for Spack to really be able to test, build parallelism, and performance. Ninja is very good, and especially at large scales like this. So what is our problem space? So right now, as I mentioned, we're a mono repo, and I think if you Google in the internet, I'm not going to get into the debate of mono repo versus distributed repo. There are advantages to both. Right now, we would like there are requests for us to have per package distributions. Sometimes certain code teams are ready to do things others aren't on certain systems. We'd like to be able to do that, deploy them easier. We also would like an easier way to interface with external codes. A lot of times they say, oh, well, I want to partner with Sierra, I want to link with Sierra, but really they just want to link with the physics that they're interested in, like thermal fluids or structural mechanics or something like that. And then another thing is it's nice to kind of everybody be together, but there's not a lot of agility between teams. A nice example of this would be one of our builds. We build with O2, and the reason why is because there is a single package that won't link out of the several hundred packages there with O3 on, but everything else will build. And we discovered that as part of this work that we're doing now. So basically, we'd like to get this while still kind of preserving or improving a lot of the great things we have, like our coordination, the way that we can kind of make everybody update together with TPLs, the build speed, our ability to have kind of monolithically verified CI throughput, testing and reporting, and a good developer experience. So what does this look like? Well, when we got together and decided we're really going to do this, we said, well, let's try to CMake and Spackify this whole thing. So this is just Sierra by itself. This is none of our TPLs. All of our TPLs are split out from this. And Spack obviously was very attractive because some of the things that are pain points for us right now, like distribution, modularity, and external, like dependency management, it does very well. And the big open questions here that we're working on right now is, can we get the build performance we need? Can we get our process performance in terms of like our CI throughput and these other things? And the developer experience, which I'm not going to talk about because that's a whole other talk by itself. So let's start walking through. So we came up with this idea. We basically said we have these like jam files that we can orchestrate packages around. And we just set up a process to start doing that. And the first thing we hit was we just started setting up packages. And the very first thing is it took forever because the source code is massive. And so just the basic implementation of saying, oh, we're going to use this Git repository. Well, each package, we're basically ending up now with 100 clones of even single depth Sierra is still several gigs. And it's still taking several minutes to do. So our stage time exploded. We're filling up every scratch disk that we try to work with. Luckily, there's already tooling out there. And there's a great blog post about this, about bringing down the size of your monorepo. And so we basically put together an implementation of adding git sparse checkout into Spack. This is a merge feature that we contributed. And you can basically apply git sparse paths, and it will only check out the source code you need. And so now your monolithic repo becomes only the source code that you actually want. And it was an order of magnitude savings for us. So we went from a 7-minute stage to 23 seconds, and from 2.2 gigs to 36 megs. So at the end of the day, we end up with 1 clone of Sierra instead of 100. Which is great. So with that allowed us to kind of move into the build performance realm and say now we can start to move more aggressively. And I think this has been hit on a lot already. Kathleen did a great job talking about it, and a lot of people have referenced it. We've driven all of this, and we kind of have to rely on the dep files, and you'll see why in the next slides. But we generally, like the idea is, yeah, you want to have this job server, you want to have this queue. We actually, because we tend to just put all the resources we can in, a lot of times we don't need the job server because we'll just let the OS page and handle the overload, and it does okay for us. So if you're not actually trying to throttle back resources, in our experience, you can just pound the machine and get a pretty fast build. So what does this look like? We know here that we are injecting a whole bunch of overhead into our process. And when I showed my own team members this, they told me, you fabricated this data. And I will say I spent a lot of time on this. The orange curve here is if you just do a Spack install of the build, and we're going from 15 to 30 to 60 to 90 cores. I should have done this as a log plot, but I didn't because I didn't think about it. But so in this case, this is on a local scratch disk. And what we can see here is Spack install, where you're not amortizing these costs, is a lot slower. And in this case, the make job server can amortize the cost well, or just parallel instances. And here we are using Ninja. We're using the kitware Ninja coupled with make. We get dramatic speed ups with Ninja. So when you look at this, I ran this a few times, and one of the things I learned, because we almost never try to throttle it back, is it's kind of harder to restrict the build with these kind of parallel job launches. And I'm looking forward to when this is all native to Spack install. I will say I don't expect every time we run this that we're going to be like right on top of the monolithic build. But our statistical data for our CI shows that we are matching the monolithic build for our processes right now. There are some caveats here, though. Do I talk about it? And we'll get to those later. OK, so when we look at the build, this is what it looks like. We can actually take every node, and this is what we've done is we've computed the average. So in this case, each node is taking an average of 33 seconds to go through the configure, build, install, post-install phases. And then the biggest node in here is about 6.5 minutes. This is with 90 cores. And so we can kind of see, and I could produce another graph that shows you, how efficiently are we marching through. Luckily for us, we have plenty of work to do, and kind of the bigger apps here, we know where they're at and that they're going to hit them together. The graph structure does very much affect the level of performance that you'll get out of this type of parallelization. When we look at it, so this is the Spack install, and you can see, OK, we have another node down here that pops up at us. And this one is kind of like, it is a leaf node for us in terms of Sierra itself. And so it's much smaller with the depth file because relative to the others, it's getting all of the resources where the other ones are having to share. But overall, it is the amortization and the stacking that is providing us the speed. The builds themselves aren't that much faster individually. So the takeaways of performance is surprisingly good. I looked at that and I said, wow. And even when I presented it, our CI statistics, wow, that was really good. Black Box Ninja is a very hard thing to beat. So we're very happy with this. There are some caveats, though. We do know we're injecting more overhead into our process by doing this per package. And you feel a lot more on slow file systems, where all of a sudden the install goes from sub-second to 30 seconds, 2 minutes on some of these HPC machines. CMake can slow down quite a bit, too. It can go from 2 to 3 seconds to a minute and a half. And that really adds up. Another thing is device builds, especially ones with slower link times. We really feel that there, too, because Ninja can do an additional level of amortization that we can't do with the per package Spack parallelization. And then finally, overall, the process is good, but we're not competing yet on the incremental build, or only in certain sub cases. OK, but overall takeaway is I'm happy. That makes me very happy. So now let's talk about where we're going next. And this is kind of the current bear that we're working on, is how do we get our build and test cycle to be as efficient as possible and to expose a lot of the new features that Spack provides us. So for Sierra, essentially, and I think this is, I've made kind of a dummy graph here, but we have kind of a basic process, and this is probably similar to just about every other code in this HPC space. So in our process, we're going to do a build. We're going to build out our graph. And when we get there, we're going to want to report that somewhere. And then we're going to have a series of regression tests that we're going to want to run. And this is how we validate that the build is still correct, that the software is doing what we want, and that we can sign off that we can secure our mission space, that we still have good quality of software. And so in the nightly process, we are going to run all of our tests, and it is very, very expensive. So Sierra, what we run is over 20,000 tests per night. The full suite for each build is on the order of a CPU week, usually a little bit more, and we're running dozens of lines a night. We're probably over 50 lines. And this is kind of something that we really have to do at this point. It would be nice to say we just could unit test everything, but with a 20-year-old code and many of these practices being developed, that's just not a reality. And so I think this is an area where I would like to see better potential integration with Spack. I know we have some kind of testing hooks, but really we treat this as a separate process because we require an HPC resource just to run our tests. And it doesn't currently integrate well with the current processes. So when we do CI, we want to, obviously we can't do this for every change set. So basically, the way our CI process works is we only want to build the code that was changed and then the things that are downstream or upstream of it that we need to basically build or to verify we haven't broken something that depends on it. And so we have this process where we detect, based off of the change set, what we need to build, and then we identify in the test suite what it is that we need to test. And we have actually a very complicated setup for this that probably deserves its own talk, and maybe it will be another sort of instance here. Now, this is where we're starting to get into. So that is the current state. One of the things that Spack enables for us is, and packaging it out like this, is we have the ability now to start to inject build time tests that hook in very naturally with Spack's hooks. And this is something that we are excited about. We've basically added in all of our unit tests for all of our packages as something that when we do -- test root, it will run them and then it will give us a fail fast. And the argument here is if we can free up more resources, because even though we have a lot of resources, the scope of the project, we still feel very resource constrained. I mean, the US government could spend a lot of money and we would still be hungry for more. So this is actually looking very nice, because even as we've been doing our Spack builds, we have been able to add in a level of verification that the builds are correct without even having to get too deep into the regression test suite yet. Now the next obvious kind of thing is, well, what if we could add in a binary cache? And just not have to do as much building and just start with the change set itself. So there are some potential savings here. It's not 100%, right? You have basically your savings would be what is the cost of building this upstream versus the cost to query from the cache, fetch over the network, and unpack on your file system. But that's still savings for sure. Now, at the first, in the state today, and the way that we're working on this, we're always working off of some branch as part of our CI process. And so there's an issue here that if we just naively throw like our develop branch on this, these binaries are not unique. They don't actually have complete provenance. This is something that's been missing in Spack, and we are trying to change that. It's basically, how do I distinguish develop today from develop tomorrow from develop 6 months from now, right? That's kind of the question here. So we do have something, Robert alluded to it. There is this kind of, you could inject the git at SHA equals develop version. And this works, I mean, this will work. We have run into some problems in that certain processes and some of the automated tools don't like things like the equals character, and it will break the paths and stuff like that. But the other kind of thing here is that when we're trying to target things like reuse and just making things, or not necessarily reuse, but when we're trying to target the binary cache and stuff, we just think there can be a cleaner way. So where we're moving to is there's this commit equals SHA, which we can inject. And now when we do this, we will have complete provenance, and we can know that this binary is unique and correct. So the question here is, can we do better still? With Sierra, if I change the commit, I'm changing all 100+ binaries that I now have to push to the cache. And really, the only thing that changed was this red blob here. So our next step was basically to say, can we add a utility on top of this, since we have the git sparse paths already, and they're embedded in the packages? Can we just use that with Git to basically tell us what is the last commit where that package actually changed? So that way packages, especially these type of packages that don't change very often, they'll just sit in the cache, and we'll basically never rebuild it until either somebody makes a change down here or they make a change here. And so what this does is it basically allows us to reduce the amount we have to push from and manage the cache by at least an order of magnitude. So how we've handled this right now is we've created an extension because in order to get this information, we do need a copy of the source code directory. But with this, we can basically just run this, and then it will add the commits to all of the specs in the environment as a property of these are the commits that I want you to work with. And so, yeah, this is essentially the future of where we are looking to go. And working well, it basically has the potential to make it to where the nightly process is just unpacking a build cache and running the tests. We're not even building anymore. Okay, so conclusions. I know I'm running a little over here, but I'm the last speaker, so. So, you know, I think there's a lot of trade-offs. There's a lot of fierce like Reddit debates and stuff about monorepo versus distributed repo. And I think this is one of the things that I'm most excited about is, to me now, I like with this sort of tooling and using Spack, I don't really care anymore either way. Like we can get some of the advantages of both. And I mean, this elusive, can we have our cake and eat it too? I feel like we're close. I feel like maybe I'm a little too excited. But I think we're going to get a good chunk of it, maybe not the entire cake. Where are we at in terms of what Spack is providing that's making this happen? The Git management integration, gold star. I think we've pretty much hit what we need to there. The build parallelism, I think, is on the way. We're doing well, and I think Kathleen's PR is going to be really important to that. Testing hooks and stuff, I think it's very good. We're seeing a lot of benefits, but it would be nice to be able to integrate more cleanly with a larger test suite. Binary caches, I think, are good, especially with the recent changes. Binary provenance is my thing. I need to finish it off, but we'll get there. That will turn green soon. And then distribution, containerization, and extensibility. After my first talk, I might move extensibility to a yellow. I do think the shell script extensibility would be pretty nice. But overall, I'm very happy with what we can do with Spack and the level of software quality we can preserve. What is keeping me up at night right now when I think about really getting this to be Sierra's primary build system, deprecating and deleting the old one? The file system sensitivity and kind of the vulnerability that injects there is a concern. And I realize there's a certain part of this that we're just never going to overcome, but whatever we can do there is definitely appreciated. The database searching and reuse is something that I don't think I'm that worried. It kind of just lives in the back of my mind. We don't really use reuse in our environments because we don't want the concretizer making choices. We want exact matches all the time. So we don't have to worry about some of those penalties. But I can see scenarios where we would want to, and then I do worry about kind of the scalability, the cache management, and garbage collection abilities here. Like how easy is it to go in and clean up a cache when you're pushing a ton of packages and a lot of data up into the cloud. And then the final one is kind of the developer experience. We really want to develop as we're testing and testing as we're deploying to kind of complete this circle and have one workflow. I think we are like 70% there. There's just some cognitive dissonance there for developers that we have to figure out. But many people have already talked about that. I've talked about that. Overall, I'm very happy. And that's it. Thank you.
Okay, I'm going to steal the first question. I forgot what I was going to ask it. So, okay. Are there any questions for Phil? Anybody? No. Okay, no questions for Phil? Yes. I knew there'd be questions for Phil. Come on. All right.
It's a statement, but I don't remember if we've talked, the cache management garbage collection is potentially implementable outside of Spack if you use the OCI cache. Like several container registries have built-in time-based garbage collection, so
yeah,
no promises, but that was my idea for where we would go. Like for a very easy to implement, we'd get most of it solution.
So that's semi-true. Part of this is I had a discussion on that, and I think they need to do some more work there. They will attempt to clean up your cache and for a set window of time, and then they give up. And so if we are pushing at a rate much faster than they can clean up, then we'll flood it.
So your binary provenance proposed extension there is very interesting to me because we version our packages by git commit, and so it would be really nice to have an automatic tool. We did this because GitHub tar files are not completely stable.
Yeah, I mean, this has been a hobby, like this has been something that bugged me for a long time, and I always gave Todd a hard time about, and then I finally just, he was like, go fix it, and so I started working on it.
More work than you thought it was.
Substantially more. Like, I was really hoping that I would be showing you, like we have all of the pieces in place and we've done some kind of demo runs, but we haven't turned the final thing into production yet because the syntax and all of, like looks like a small change, but in terms of the implications of what it means for versions and Spack models, I mean, we have iterated, we've had multiple meetings, lots of discussions. Like it's relatively few lines of code, but a very big impact and change. So
we got philosophical, right? I mean, we were
yeah.
on a call saying, what is a version? Like,
right, yeah. Like, we're questioning everything, so.
Yeah, you want to go ahead? Oh, okay. So I did have one more question on your file system sensitivity.
Yes.
So for that, is that like, are you talking about file system sensitivity of like the installs themselves being big, or are you talking about like the concretizer reads 8,000 files and and all the sensitivity on the Spack side?
Both.
Okay, both. Well,
so
there's one of them I can do something about. So
right. So that one is important in terms of like the user experience of, hey, when I go to run, like if I just updated Spack and then I have to lstat all these files or anything like that. But so a good example would be we have some teams that are targeting an HPC system and they only have access to a slow file system. And we see 1 to 2 orders of magnitude difference in terms of the amount of time and the install phase takes for these packages and also potentially the CMake configure.
Yep.
So it's just, yeah.
Okay. Any other questions for Phil? Okay, I have one more, and then we can get out of here. This one, so does this PR include the resolving branches to the latest commit thing with Fresh, or is that a follow-on?
That's going to be, so that will be a follow-on, but probably very quick. So
yep.
The context here is this will enable this commit SHA for you, and there are rules for it, and that the concretizer will respect, so you can't just willy-nilly assign it. The follow-on is that we have to then make sure that we have compatibility with the source mirrors, and then I've already implemented and tested that we can basically make, when you do the solve, Spack will go look up what the commit is at the time that you concretize and say, this is what you're building right now. And then that will then be what you fetch and build.
And then we'll get full reproducibility on the specs for this.
So that'll be the native behavior, hopefully before 1.0.
Okay, awesome. All right, well, let's thank Phil one more time. And